Hello everyone, welcome to ilustraca. In this lecture, we will see the stiffness modifiers provided for wall sections in ACI 31819 and how we can implement that in ETABS software. So here you can see I have modeled two walls, okay, two walls, and what I have done, I have applied some load here. So some lateral load I have applied. If you see here, display load assigns joint, and you can see this is the lateral load that I have applied. So for this wall I have applied 100 kilonewton load, and for this particular wall I have applied 300 kilonewton lateral load here, right? So now if I jump into the code ACI 318, here you can see this is the table that we'll be following. It is table 6.6.3.1.1a, which is giving us the moment of inertia for cross-sectional areas permitted for elastic analysis at factored load level. Okay, so remember this is said that factored load level, right? So that means these modifiers shall be applied for when the load is at the ultimate level, not at the service level load, right? So now if you see that there are columns, walls, beams, and flat plates. So for all these elements, the stiffness modifiers are given, or you can say modifiers for the moment of inertia are given. But for the wall, there are two modifiers given. One is 0.7 times the IG, gross, you can say moment of inertia, and one is the 0.35 times IG, that means 35% of the gross moment of inertia. So now, which one we should consider when? So to understand this, we need to read this commentary. So if you just read this commentary here, I will just mark it. So if you see here, it says that, let me take a bigger, yeah. It says that if factored moments and shears from the analysis, I don't know whether it is clearly visible. Let me, yeah. You can see here this particular para. So if the factored moments and shears from the analysis based on the moment of inertia of wall taken equal to 0.7 Ig. So from that, what we understood that when we'll be performing the initial analysis, we need to consider the moment of inertia of the wall, which is, you can say, responsible for resisting the particular load that you are applied. Okay, so we need to consider that moment of inertia as 0.7 times the Ig. That means 70% of the total moment of inertia we should consider, and then we should cross check that if this particular section under the factored loads indicates that the wall will crack in flexure. Okay, obviously when we have applied some load, whether it is in plane or out of plane, there will be deformation, and we need to check whether, I mean, flexural deformation will occur, and we need to check whether it is cracking under the flexure based on the modulus of rupture. So that means what we will see that due to the we'll find out the tension due to the bending, tensile stress due to the bending. Okay, this is what modulus of rupture is, right? So tensile stress due to the bending, and the stress developed shall not cross the modulus of rupture. If it is crossing the modulus of rupture value, then what should we do? The analysis should be repeated with I equal to, that means once we had this is equal to I1. Now if we have some areas where the tensile stress due to the bending crosses the you can say permissible limit, which is the modulus of rupture, then in that case we need to consider that this I2, the next I2 should be 0.35 times the total gross you can say moment of inertia. Okay, so first we will try with 0.7 times gross inertia. If it cracks with respect to the modulus of rupture, then we need to analyze with 0.35 times Ig. Now, do we need to apply this 0.35 times Ig to whole length of the wall or whole height of the wall? Not length, sorry, whole height of the wall? No, actually. If you see here, it says that in those stories where cracking is predicted using the factored loads. So in those stories where the stress has crossed the limit of modulus of rupture, so in those areas only we need to apply the reduced moment of inertia with 0.35 times Ig, and we need to reanalyze the structure, okay, of the wall. So now let us see how we'll be implementing it in our software. So first of all, what we understood, we need to go with this uncracked moment of inertia, which is 0.7 times Ig. So initially, whatever moment of inertia, suppose see, this is my wall. If I draw a cross section, this is my wall, right? Okay, this is a very simple rectangle. This is suppose the D. This is suppose my thickness T. Okay, and the load is applied along this direction. Okay, this is my factored force, you can say, right? I would say that this is my lateral load which is applied in this direction, and this is at the ultimate level. So in this case, the moment of inertia which is responsible for you can say uh, uh, responsible for resisting this particular force. This is what for when we provide shear walls for, actually, so to resist the lateral forces mostly. So in this case, the moment of inertia which will be resisting this force will be what, uh, T d cube by 12, correct? Because this is the major dimension which is responsible for resisting this particular force. So generally we say bd cube by 12, correct? So here this is my d and b is actually the thickness of the wall. That's why we can write it is as t d, or if I just make it, suppose the length of the wall, if I just write it as such as L, so in this case it will be uh sorry, T L cube by 12. So this is the moment of inertia which is responsible for resisting this lateral load. Now, so what we understood, that this is the I suppose measure, as this is the major axis or having the higher dimension of the wall. Now, do we need to reduce the moment of inertia in the minor direction also? Okay, this is the moment which will be moment of inertia. Do we need to also reduce this moment of inertia? Okay, that means I minor, suppose I major, I minor, that means L T cube by 12. Do we need to reduce this also? Now it depends on how you are considering or how you are designing the wall. Okay, so if your wall is the only element which is responsible for resisting the lateral force, and also it is load bearing, suppose you have also beams connected in the perpendicular direction, so obviously this the load on this beam or the slabs will try to bend the wall in the other direction also. Suppose this is my wall. Okay, so generally this is the kind of in plane bending we are expecting, through which it will be resisting the lateral forces. But if it is also bending in the other direction, if there is a chance of bending in other direction, I mean the minor axis, due to the suppose connected beams and floors there, so in this case you need to consider that stiffness also. Okay, that stiffness also, and design the wall for the out of plane bending as well. We know shear walls mainly are stronger in the in plane bending because of the higher dimension, and very weak in the yeah, out of plane bending. So if you want to design the shear wall for the out of plane bending depending on the loading condition, then in that case you need to consider the moment of inertia in the out of plane bending direction also. Otherwise you can make it negligible, you can make it very negligible. I mean, we are not reducing it to 0.7, we will be reducing it to 0.1. That means we are not designing the wall for taking the out of plane bending. So in that case, what will happen, the loads will be redistributed to those elements which are having out of plane stiffness higher than this particular one, right? Because we have, when we are making it 0.1 times or 0.01 times the moment of inertia, so what will happen, it doesn't have much stiffness to you can say take that out of plane bending out of plane loads, right? So in this case, suppose you have columns there, so obviously the columns will have, suppose this is my column, so this will have both this axis and this axis stiffness, right? So what will happen, the loads will be redistributed to those nearby adjacent columns, and those columns will be responsible for taking those loads. Okay, so or the for resisting the out of plane bending. So now it depends on how, what design philosophy you will be following. For now we are doing 2D analysis on the XZ plane, so it doesn't matter whether I reduce or keep the you can say the out of plane bending moment, it will not matter in the analysis results. Okay, so okay, let me now go to how the part where we'll be assigning the factor of the stiffness modifier. So let us select these walls. Okay, let us select these walls. Now let me unlock this first. Okay, so let us go to assign shell, and here you'll be finding this option called stiffness modifier. So as I said, if you are designing the wall for out of plane bending, so first we have F11, F22, and F12. So remember, F11 is nothing but the stiffness, which is this axial stiffness. So this is my 1 direction, this is my 2 direction. Okay, this is the axial. The F11 defines the axial stiffness, and F22 defines the lateral stiffness. Lateral stiffness. Okay, so when you have this load, and obviously it has some self weight of this particular, or some gravity load also on this. So what we will do, generally we'll be reducing these two aspects of the stiffness, F11 axial stiffness and F22 the lateral stiffness of the particular one. Okay, but if you are also designing the wall for out of plane bending, okay, then this will also come into picture. So we will make this as 0.7, 0.7. If you keep 1 means it is the full stiffness. Okay, it is not the reduced stiffness. So you can, if you keep it 1, that means it will take higher load in the out of plane direction. Okay, so what we are doing, if you are designing as per the codal provision, if you are designing the wall for out of plane bending moment also, in this case all these will be changed to 0.7. If not, if you are not designing the wall for out of plane bending, only designing the wall for in plane bending, then this shall be reduced to 0.1 or 0.001. Basically the concept is to make it almost zero. Okay, that means the wall shall not take any out of plane load. Whatever load is coming, that wall shall not provide resistance to that, so that the load gets is distributed to the nearby components which are responsible for taking those out of plane bendings. Okay, so we'll make it 0.1, 0.1. In here, as we are performing in plane you can say 2D analysis, so doesn't matter whether we keep it 1 or we keep it 0.1, it will not take in out of plane bending, because it doesn't have a out of plane, right? So it's just one single plane, 2D plane, X and Z, correct? So now for our case it is 0.7, 0.7 for only F11 and F22. What about F12? F12 is nothing but the GA shear. So sometimes some of the engineers also consider that the shear stiffness of the wall will also reduce due to the cracking, but the code has only mentioned regarding the flexural stiffness, not the shear stiffness. Okay, so you can keep it intact whatever it is, but these two values will be reduced to, initially will be reduced to 0.7 times the IG. Okay, 0.7 means it will be multiplied with the gross moment of inertia of the wall. Okay, and gross moment of inertia in terms of, one is for axial stiffness, another one is for lateral stiffness. Okay, fine. Secondly, if you have a total building, 3D building, and these walls are also load bearing, in this case these will also become 0.7 and 0.7 and not 0.1. If not, if there is columns provided to take this loads, then you make it 0.1, not 1. You do not keep it 1. Okay, so our case, what we will do, we'll make F11, which is the for axial stiffness, 0.7, and F22 as 0.7. We do not have, again I'm saying, we do not have a out of plane you can say axis, so that's why we are keeping it 1. Otherwise I would have made it 0.1, 0.1, okay, or 0.7 or 0.7 based on my loading condition or based on my structural system. Okay, so as of now I'm keeping it 1, but in your case you should decide whether it will be 0.7 or 0.1, right? So now let me apply. So we have applied the reduced moment of inertia in case of uncrit condition, which is 0.7 times IG. Okay, 70% of the gross moment of inertia. Now we need to analyze this, you can say, walls, right? So what I will do, I will click on front analysis. Okay, so it is very clear that when we talk about the axial load, you can see it has a huge uh, height of this particular wall, right? So the moment of inertia for this direction, for vertical direction, is huge, correct? So we do not have to check the you can say stresses for that particular case. Our load applied is in the lateral direction, so basically we'll be checking the stresses for the in plane action, in plane bending action, right? So this stress, as this axis is 1 1, this axis is 2 2, so this stress will be basically S22. So we'll be checking the S22 with respect to which load? With respect to the lateral load that we have applied. And remember, it needs to be in the ultimate level, not in the service level as per the code. Okay, so now what we will do, I will go to here, you can see show shell stresses and forces, display shell stresses and forces, and the load case will be lateral. Here from the component type, you need to check, create this one. You need to select this one, shell stresses, and we'll be selecting S22. Let me go with S11 first. I'll click on display deform shape, and if you see here, let me make it 0 0. Why it is 3.25, I will tell you later on. So if you see here, now these values are very less, you can see, because as I said, there is no load and the stiffness of on along this direction is very high. If I talk about the lateral direction, so this is S22 for the, sorry, I have I should have used dead load. Yeah, you can see nothing is much changing. Okay, so now if I go to lateral load, shell stresses S22. So now you see here, let me make it, okay, S22, fine. Now if you see here, this stresses here, it is changing. You can see the you can say values here. Okay, the what should I say, the range of values are given, so you can see, we can see these stresses. Now how to understand, that what is the limit of stress, up to what extent we should consider 0.7 Ig, and up to what extent we should consider 0.35 Ig. So for that we need to find out the modulus of rupture, right? So if you go to, I think, 19.2 point something, let me go to 19.2, and yeah, here 19.2.3, if you see, so the code is giving the modulus of rupture value, which is Fr equal to 0.62 times lambda into root under Fc prime, right? Fc prime is the cylindrical strength of concrete, and I can say lambda is nothing but, here you can see the lambda value that we'll be considering for the normal weight concrete, it will be 1. Okay, if you have lightweight concrete, then you need to consider this particular table, but for normal weight concrete we can go with the fact the value of lambda as 1. Okay, so it's a modification factor. uh, so in our case it will be 0.62 times root under Fc prime. So let us jump into the model. So the Fr value that we'll be getting, it will be 0.62 lambda root under Fc prime. Okay, so now we considered Fc prime equal to 4000 psi. Okay, 4000 psi, which is around 27.58 MPa or Newton per mm square. Okay, so Fc prime in SI unit, if you see, we are getting around 27.58 MPa for the 4000 years psi concrete. So the material that we have considered is 4000 psi concrete. Okay, so it is, if we convert it into Newton per mm square or MPa, it will be 27.58 around. Okay, so in this case, how to find out the Fr? So the Fr in Newton per mm square, it will be 0.62 times 62 into 1 into root under 27.58 Newton per mm square or MPa. Correct? So let us calculate this. How much you are getting? 0.62 multiplied by 1 we do not require. root under 27.58. Okay, so we are getting 3.26, you can say, equal to 3.26 Newton per mm square. Okay, so this is my modulus of rupture, right? This is my, I should say, modulus of rupture. Now, what is this modulus of rupture? Is nothing but the tension due to the bending, right? So now you can see the stress, the limiting stress value that we got is nothing but 3.26 Newton per mm square. So we need to find out the areas in the wall which is subjected to the ultimate load, whether it is crossing this value of stress or not. So if you see here in the first case, here it is, you can see it is more than 3.26. So after the first floor, it is reducing. Okay, so you can see here up to this value it is 3.55, 3.2, 3.9. Now it is reducing. So up to first floor, you can say, sorry, second floor, first and second floor, the values are you can say more than 3.26. Then after that it has reduced to 1 or some less than this value. So that means we need to reanalyze the wall considering 0.35 times Ig only for these two stories. Rest of the stories will be analyzed for 0.7 times Ig. Correct? In this case, if you see, it starts from here, and if you see here up to a you can say considerable height, it is more than 3.26, and after this it is reducing to, you can say, less than 3.26. Now seeing this in the contour like this is very difficult, right? So how to do this? Now what you can do, you know the limiting value, which is 3.26, right? So you can put this minimum and maximum range both as 3.26, 3.26 and 3.26, 3.26, and you can check which areas have crossed the limit, which is more than 3.26. Correct? So I'll just click on apply. Now you can see this red areas, or you can say magenta areas, these are basically less than 3.26. Okay, and these blue areas here are higher than 3.26. So you can see, now you can easily understand that in this case, in case of this wall, only up to the second floor we need to analyze the wall with 0.35 times Ig, and in this case up to the fifth floor, because this much part we cannot leave, right? So up to the story 5 we need to analyze this whole wall for 0.35 times Ig. Okay, so now what we can do, we need to reanalyze. So for this up to second story, for this up to story 5, so I will go to undeformed shape. I will unlock this. Now what I will do, I will select these two stories of wall, and here up to the fifth story I will be selecting the walls. I will go to assign, I'll go to shell stiffness modifiers, and I will make it 0.35. Oh, sorry, this is not 0, this is O. 0.35, and I'll make it 0.35. So now this is the cracked modifiers, because we found that these areas have cracked with respect to moment, I mean, you can say modulus of rupture. So this is my for cracked modifiers, which are defined in ACI 31819. Correct? Okay, so now what we will do, I will click on apply. As I said earlier, that when you have this 0.35, again, if you are designing the wall for out of plane bending, you also have to check for the out of plane load, and if it is applicable, then you have to you can say assign this here also. Okay, so generally walls are designed for the in plane bending only. So what we will do, I'll click on apply. I'm not reducing it. Why? Because we do not have a out of plane bending moment. Okay, otherwise I would have made it 0.1 most of the cases. So I'll just click on apply. Okay, and now we can reanalyze, and now this wall is ready for the design. Now whatever force you will be getting from this wall, you will be designing it for, I mean, for that particular force only you will be designing the wall. Okay, the stresses obviously it will vary now. This will be always there, but the if you have reduced the, you can say, stiffness of the walls, now this loads will be redistributed to other elements of the structure. Okay, here it is a single wall, so that's a different thing. But what will happen, that when you have reduced the stiffness, the force will be redistributed to, because you have reduced stiffness means it is taking less force, so that force will be redistributed to the other elements of the structure. Okay, so which are having higher stiffness, correct? So this way you will be analyzing the wall, and this way you will be applying the, you can say, the stiffness modifiers defined in ACI 31819 for the wall sections. So I hope it is clear to all of you. If you have any doubt, always write me in the, you can say, comment. I will try to solve those as soon as possible as per my understanding. Thank you, and we'll see you in the next lecture.